or crash the application? Is anyone confused? Let me move this over here. Participants. Okay. And we're recording. Okay. Does anyone have any questions on this? Okay, so again, what I'm gonna do is I'm gonna save this, okay? I'm gonna run this and I'm gonna make sure it works. So day of OSCP comes, oops, what did I not do? I didn't run it as an administrator. Run as an administrator, yes. Attach, sync breeze, release, go back. Chmod plus X example 192.168.145.10, run it, sending evil buffer, and let's go over here. Applications paused. EIP overflowed with 41, 41, 41, 41, all of our A's, and ESP has had data written into it, A inside. Okay? Questions on that so far? Okay. Please ask, because it's going to get, it's going to obviously be a little bit more complicated now. So let's restart Sync Breeze and go back to the next step. The next step from here was we need to know because we just sent a bunch of A's, right? We want to know which 4 A's represent the 4 A's inside of EIP. So I'm going to go ahead and I'm going to reattach this as Sync Breeze. I'm going to come back over here. I'm going to run nano on my example. And before I actually do this, I need to create sort of, if I set a bunch of A's, it's hard to tell which set of A's, is doing this. So what we did was we used MSF pattern create with a length of 1,000 in my case, right? Because I know 1,000 will crash this application, right? And that's the size of my buffer. We don't want to be playing with 2 variables at one time, right? So we're keeping the buffer length the same. I'm going to do this to generate a length of 1,000. Here's a length. This is a string of length 1,000. I'm going to copy that. Nano into example.py, right? I'm going to comment out my input buffer for now. Oops, right? Input buffer is equal to a string with all of this, just like that. And now I'm going to save. Questions on that? I generated our unique pattern and I replaced my A's with that unique pattern of the same length. Cool. So now I'm going to go, I got to make sure I unpause this because I didn't unpause it. I'm going to unpause it. And now I'm going to run it again. This time, when the application crashes, you'll notice that instead of it being a bunch of A's inside of ESP and 41, 41, 41, 41 inside of EIP, we have some unique combination of characters, which I don't know. I mean, I can identify 42 as B, but past that, I'm going to have to figure out the rest of this, right? So I'm going to right-click and copy this selection and use the sibling library, which is MSF pattern offset, and query it for the values found within the EIP register, 42, 30, 61, 42, which comes back saying that there's an exact match in this pattern at position 780, which tells us that EIP is at position 780. Now, we can go back to our work and update by, first of all, removing this, right? Bringing this back in. And again, I like to be very specific about how I write this. So I'll say start padding is going to be a bunch of A's times 780. I'm going to have EIP, which I'm going to define right now as a bunch of B's. And then I'm going to have my end padding, which is going to be a bunch of C's times, and this is where I'm going to use size minus the length of the start padding, minus the length of the EIP, and then my input buffer is just going to be my start padding plus my EIP plus my end padding. Notice I skipped over the offset part this time because maybe you forgot about it or missed it. I'm just showing you another way of doing it. right? So does everybody understand what we did? We located EIP. We found it by using a unique pattern with pattern create. We then used pattern offset, given the values that we found in EIP, to look it up with pattern offset. I found that that was at position 780. So I said, let's start with 780 A's, leave 4 B's for our EIP register, and let's assume the rest, the C's, flow into our ESP register. As we know, that's not the case, but we'll get there, okay? Does everybody, any questions on what I've done here so far? Once I've replaced my pattern, I need to test this again. I'm serious. You always want to be testing. If you don't test at every single step, you got to go back to the beginning. If you have if you can crash, have any of you been in the situation yet where you've uncrashed it or made it so it doesn't crash? If you've done that, you know that you're in bad shape because now you've done something that like is forcing you to go back a couple of steps because you're not sure where something went wrong. Another good tactic here is to make a copy of the Python file every single time that you use it. Okay. So I'm gonna go ahead and I'm gonna save this. I'm gonna go ahead and restart this operation. Stop, start. Run as administrator, yes. Okay. Reattach the sync breeze application, release the process, and run my example again. So now I'm gonna clear, run my example again. I should see the crash now with all B's at my EIP, because there's only 4 B's. Notice I didn't select like another, like EIP gets its own 4 characters. So we know if we see, 3, B's and an A or 3 B's and a C, we're 1 letter off. You see what I'm saying? We want to make sure we know exactly where it is. And you'll note that ESP got filled with my C's. Now, you might not notice this, but it's always worth following this in the dump. And you'll see that we have a bunch of C's. If you go up by 1, you'll notice that we've lost 4 C's from where EIP is pointed. Do you see that? EIP is pointed to a position after those 4 C's. Listen, if you skip this step, I'm going to point out something else later on that you can do to make sure you cover your butt in case you miss this. But if we can account for it, it will be better. And it will guarantee us, more precision, if you will, okay? We will add some padding later on at the beginning of our malicious payload that will allow us to not have to worry too much about this. But if this buffer was, 32, I don't even know how it could possibly be that large, but let's say it was there was a ton of variables to this function or something, because the reason why you have this parameter is because this function takes in 2 variables, by the way, username and password. If it only took in 1 field, you wouldn't have any buffer right now because whatever, who cares? But if there were a lot of variables, then there could be a lot of buffer. So in this case, accounting for 4 could be good. So I'm going to go back. I'm going to update my code once again. Control C. nanoexample.py. I'm going to update this once again. I'm going to say my offset is equal to a bunch of C's, and I'll say even C times 4. And then I'll update this to say D. I'll use this now as the size of my length, padding, the length of EIP, and the length of my offset. Cool. Questions on this so far? Okay, good. Oh yeah, actually there should be a question. Nobody caught this. This is why we always test, right? And we check each step because I almost forgot to add offset back in. And we would have accidentally shortened the buffer, which might brought us under the threshold to this is why you have to be so careful. If you can know this process, 25 free points. I'm telling you, I know it sounds like a lot of stuff to do, but it actually, once you get it, it's very recreatable. It's very redoable. It doesn't change very much. And that's really nice about it. Okay, so this is where we were at. Are there any questions? And again, if I'm you, I'm gonna go ahead and I'm gonna test this again, right? I'm not taking anything for granted. I'm gonna stop, I'm gonna start, I'm gonna make sure that this is working. Oops, run as administrator, yes. File, attach. Release. Okay. Running, sending it, Now we have a crash, 42. Our Ds are inside of ESP, right? Let's follow this in dump. It's still crashing as expected. And we have BBB, CCCC. Cool? So everything's looking good. The next thing that we realized is like, there's no point in even really continuing, right? If we can't physically fit a malicious payload, right? And I've told you, just so you have this knowledge, that a malicious payload can be anywhere between 300 and 500 because that's the standard size of a reverse shell, okay? So right now, we only have room for about 200 Ds or 200 bytes. That's not enough. Right? I want to try to increase the size and explicitly try to increase the size, right? Like I'm not accidentally doing this. I'm not trying to do this and figure out offset at the same time. I'm only going to try to figure out if I can increase the size. So I'm going to go ahead and I'm going to X this out again, restart the entire process once again. Oh God, not software protection. Sync breeze. Okay, sync breeze, start it up. Run as administrator. Yes. And then we're going to increase the size to 1300. To save some time, if you remember, I did this in the last time, nano on POC, that's the way. So this is where we were at. We had to increase the size to 1300 and we found out that we can now fit 1300. Okay, is everybody caught up to where we are logically? So what I'm going to do now is I'm going to send out this as the next snippet that we have here. I think I'm missing some stuff, aren't I? Yeah. Okay. Yeah. Okay. All right. I'll send this. I'll send this out after. So let me go ahead and make a copy. So copy poc.py, and we'll call this like verify payload size.py. That's where we were at. Okay. So now the next thing we need to do, everybody, and this is where this is going to get a little weird, is we need to actually we've now verified that we have enough space to put a malicious payload. We also verified that we have control of EIP. So now we need to actually figure out if we can put a malicious payload in that area. And what are the restrictions? Some variables and some things and some actions mean different things in different applications. What do I mean by that? For example, encoding is different depending on like what you're doing. So, you know, the number 42 could mean the number 42, or it could mean B, depending on whether it's being read as a letter or a number. Does that make sense? Like the context really does matter. And so within the context of this application, some characters or opcodes, because we're dealing with like operation code level, like binary level, some characters are actually considered to be bad characters. They're bad in the sense that they screw up what the application is trying to do or the execution flow of the application. They can do so for a wide variety of reasons, from A, redirecting the flow of the application, to B, causing early truncation of a particular character. So for example, if you remember %00 in PHP, right, is a null byte or termination character. Right? Do you guys remember this with file inclusion vulnerabilities, right? That's a termination character. So in the context of PHP, finding a null byte, if you had, you were trying to do a buffer overflow and one of the bytes in the middle was a null byte and you had 1,000,000 characters and the null byte was the 100th character, well, guess what? The machine is only going to interpret it as if it was 100 characters, right? So my point is we need to figure out which characters are good and which characters are bad. Because when we go to generate a payload, we don't want to generate a payload using any characters that are considered to be bad by this particular application. This, my friends, is the worst part of the entire process. This is very, 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 very meticulous, very painful, and very slow. I'm going to show you how to do this. It is 25 free points on your OSCP, but I'm telling you as a heads up, this is the worst and most annoying step of this entire process. Because everything before this is kind of cool. You're like locating EIP, you're locating like where, if you could fit this payload in, you're having a good time, you're figuring out like where things are. And now you need to spend time figuring out what is good and what is bad. So to figure out what are bad characters, to figure out what are bad characters, what we're going to do is we're going to include What the heck is this? Bad characters. Look at this. This website was hacked. Look at that. That's wild. Wow. Let's get a list of all of the bad characters. List of all of the. We'll have to cut that out of the recording. Bad characters. Oh God. Hex. Can we get like here you go. So this is it. Okay. All of the characters 0, 1 through FF. I'm removing 0, 0, and let me tell you why. 0, 0 is always a bad character. Don't even worry about it. 0, 0 is always a bad character. So what I'm going to do is I'm going to copy this. I'm really upset because that last link used to give me the like styling that I needed for it.
Wayback Machine.
Yeah, I was gonna say.
If you grab a link, that'd be dope, but otherwise I'll just, all right, so let me nano on this. And so what I'm gonna do is I'm gonna create something called bad chars and set it equal to this. This is gonna be a problem, isn't it? This is gonna be a problem. I really don't want to do this. This is, does anyone find that link so I don't have to manually, I guess you do what you got to do. Do what you got to do. You know. Anyway, so let me explain why I'm doing this, what I'm doing. So I'm basically going to now, instead of sending A's and B's and C's and D's in our payload section, I'm going to attempt to see if I can see each of these characters in the payload section instead of just a bunch of D's. The reason why I'm doing this is because when I use MSF Venom to generate a payload later, I'm going to specifically tell MSF Venom to avoid any characters that might screw up this operation. And again, keep in mind that like this is very, very, very weird. Like what we're doing here is like at the bare bones assembly level. And so what characters are bad characters can be sometimes, and I know for a fact on OSCP, they're effectively random. Yeah, okay, so this is what I have so far. I have all of the characters from 0, 1 through FF. I've skipped over 0, 0. So I'm gonna note that I've removed 0, 0, and we're just gonna assume 0, 0 is a bad character.
Corey, I put the link in Zoom if you want it still, if there was something on that page.
Okay, yeah. I'm wondering if I, yeah, okay, perfect. This is exactly what I wanted. Yeah, this is definitely better. I'm just not even gonna take the risk that I missed the space, so. Let's use this one. Yep, okay, perfect. So this will do it for me, right? So this is all of the bad characters between 0, 0 and FF. And again, I'm gonna immediately remove 0, 0. So just take my word on that. That's a bad character, get it out of there. Everybody understands so far what I've done. I'm just pasted in a bunch of bad characters. I'm now going to go ahead and I'm gonna update this whole thing, right? I am now going to say that I want to include my bad characters, or sorry, bad chars, before I put my sort of data in ESP or my end filler. And of course, I need to make sure that I update the size, correct? So I'm also going to subtract out the length of the data, the length of my bad chars. Okay, good. Everybody okay? Good so far? Okay. So now, with all of this being said, let's go ahead and save. All right. And let's go ahead and actually run this on 192.168.145.10. And I think I need to restart everything, right? Oh, is it ready? Nice. Nice. This is cool. It's a nice find. Okay, so things are running already. Now what I'm going to do is I'm going to run my proof of concept, click enter, send the evil buffer, This should still crash the application. You'll note that it doesn't look like anything consistent is inside of ESP, which is why I can't find anything. But notice that my EIP is still cleanly overridden by 42. I didn't screw that up. If that ever changes, right, you know you broke something. You should always see your 42s in there now, right? Because our Bs are always inside of my EIP. I'm going to go into this ESP register, and I'm going to follow it in the dump. Let's take a look at our numbers. If all of our characters were good characters, we would see all of the characters in order from 0, 1 to FF. But let's take a look. We don't. 0, 1, 2, 3, 4, 5, 6, 7, 8. And sometimes I find it easier to switch it to hex 16. So you can see like all 0, like it should be 0 through like F, you know what I'm saying, in each line. 1, 2, 3, 4, 5, 6, 7, 8, 9. 0, 0, 9F. Whoa, what happened? What's our first bad character?
Zero, zero.
Not 0, 0, but you're right that it's the character that should have been in the position of 0, 0, right? Take a look at this. All of our characters, right, our bad chars, which are supposed to be the beginning of this section, right, filling in, right? We skipped over 0, 0. We had already removed that. We see 1, 2, 3, 4, 5, 6, 7, 8, 9. What comes after 9 in hex? Give you a hint. It's not 10.
A.
0A. So 0A is somehow truncating the rest of our payload. We're not even seeing the rest of them. You see this? Therefore, we should remove 0A from our payload and try again to see if we have more bad characters. So 0A is definitely a bad character. And if 0A was part of our malicious payload, we have no idea what the side effects might be. The best thing to do is just simply remove it and make sure that we generate a payload that does not include 0A. Does that make sense? So I'm going to go back to my code. And once again, go back to my code. And over here, I'm going to go remove 0A. The most important thing is that you note this as well, that you removed it, X0A, because at the end, we're going to need to know all of the characters we removed. So when we generate MSF Venom payloads, we can tell it, don't use these characters. Make sense? Okay, so I'm going to save. All right, I'm going to do this again. Come back. All right, stop the service, start the service. Dang it. Attach, sync freeze, run. And I'm telling you, this is the worst part. It gets better from here. It's all uphill from here. This is the worst part, I promise. So we do this again, we send it, we're here, we crashed it. We make sure that we didn't screw up any length of anything. EIP is still here, right? We go to ESP, we follow it in dump, we see over here. Now, 1, 2, 3, 4, 5, 6, 7, 8, 9, 0A, which we removed. So that's okay. We can skip it, right? 0B, 0C. What? I think we found another one, didn't we? Right? So back to the drawing board. Come back once again. Here we go. Nano. Let's go down here. Remove our 0D. Right? Add it to our collection of things that we're going to need to remember later. Save. Y. Yeah. Okay. I'll do one more with you all, and then I'm going to let you guys do it. So once I want to show you one more kind of thing that can happen that you need to be really careful of. Run as administrator. I genuinely, by the way, do not remember all of the bad characters for Sync Breeze. So like this is like actually, this is a genuine, this is like not, Anjali's note is so important. Do not rush this. Do not rush this. This is like again, if you do the buffer overflow, if you can get the buffer overflow down to an hour and a half, 2 hours, 2 hours is fair. Okay. You just got 25 points. You need 45 more, right? In 22 hours. Do you see how much more reasonable that is? Like this should be, like you should take your time, get this right, okay? And like actually get the points on this box. It should be a freebie. That's my goal today. That's why I'm here with you all today. I want this to be a freebie for you all. So I'm going to run this again. Oh, wait, no, I'm not going to run. Did I reattach it? File, attach, sync breeze. Okay, release. It's released. Running, run. Sending evil buffer, crashed on B's, ESP is over here, follow and dump, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, B, C, D we removed, EF, 1, 0, 1, 1, 1, 2, 13, 14, 15, 16, 17, 18, 19, right, 1A, B, C, D, E, F, 20, 21, 22, 23, 24. Look at this, another one, right? So it looks like 25 here might be bad, right? So there are, I believe, 3 to 4 more, okay? But do you see how 25 is bad here? Is that clear to everybody, right? I want to be very clear about this. There are 3 things that can happen with, I shouldn't say, there's probably more, but there's 3 that I see, okay? One is the character itself is disrupting everything that comes after it. That, okay, is the best one you have because it's super obvious, like this one. 25 is super obvious because after 24, it just like literally breaks, right? Nothing else is there. So you know, you can use that knowledge and go, very obviously need to remove 25. You also can have situations where a substitution occurs, and those are less obvious. So like, let's say you saw 24 and then 24 again, right? It would be hard to figure out if it was the 24 causing the problem or the 25 causing the problem, right? Because it could have been 24, 24, and then maybe the 25 is appearing as 24. If the number that you're looking for is appearing as a different number, aka a substitution has occurred, it is a bad number, okay? Those are less common. The other very common thing that you'll see are missing values. So in this case, 25 was extremely disruptive, but it also could have been the case where 25 just wasn't there and it jumped right to 26. 25 was an ignored character, in which case 25 would still be a bad character that you need to remove. Does that make sense? So any character that does not show up in the expected way is a bad character. And you want to be sure and not move forward until you get all of the characters. Okay. There are, I believe, 6 or 7, okay, in Sync Breeze. Your goal now for the next 30 minutes is to figure out the rest of them, okay? Take your time, don't rush. Get through 1 or 2 more and I'll be happy, okay? So I'm going to send you where we're at and you can keep going with it, or you can go back and do it from your own code. I don't care, either way. All right, I want you to learn this process, and then at 4 o'clock, we're going to move on to the next step, okay? Cool. All right. Any questions before I send you out into pairs? Feeling good? Good, good, good. Cool. All right, I promise it's the worst part, so enjoy your next 30 minutes.
Could somebody put me in the room?
Yes, I'm sorry. What, do you know who you're with? I'm sorry.
Yeah, it's okay. I was with Clara and Dawn. I wasn't sure if it was Vinny who had the control or it's just everybody disappeared.
No, it's me. I'm sorry. I'm trying to get the thing out to you also. All right, I'll put you into room 3. Sorry about that.
All right, thank you.
Okay, cool. So where are we? I'm a little ahead of concept. And I'm going to comment out my proof of concept. Oops. Actually, you know what? I don't need this anymore. So I'm going to skip past this so that we save on some time. I mean, I could sit here and do all of them, but it's going to take a little bit of time. Once you figure it out, this is the set of bad characters that you should have. So if you found this list, you did it. Good job. Any questions on bad characters before I move on to the next step? Of course, you want to make sure that you also remove this. This doesn't exist anymore. And that you didn't break anything. Questions? Okay. So these bad characters are going to have unknown effects on our shell code, but also will have unknown effects on the assembly code that's actually running. So much so that what we want is we want to avoid our bad characters entirely throughout this process. And let me tell you what I mean by that. So these are our bad characters. And what I'm going to do is I'm going to run this one more time. Okay. Go back over here. Okay. Looks like I could use another desktop. So let me close this out. Stop. Restart the service. Okay. So now that we've done that, I'm going to rerun this. Could not connect. Uh-oh. What did I do? Did it actually? What did I do?
You still have bad characters in your input buffer.
Yep, and because I'm try accepting, beautiful, perfect, thank you. Sometimes it's better to not try accept so you can see the error, right? Or just throw at least the error message in the accept block, which you're supposed to do. So perfect, I think that's it. Okay, good call. All right, so let's run this again. Yep, awesome, good call. So now it crashed, everything looks good. We have this here. Okay, so now where do we want to go from here? So take a look at where ESP crashed. It crashed at 01BA745C. Have you noticed that this has not been the same every single time? We could run this again, but it's not going to be the same. Sometimes it might be, but it won't always be. What this means is that the application has ASLR enabled, meaning that every time it's loading this into a different place in memory. This is a problem because what we could do if ASLR was not enabled, and I want to see your faces as I say this so that I get some head nods that you understand this. If ASLR was not enabled, what could we do right now to compromise this machine? If ASLR was not enabled, what could we do right now? Let's see how much you understand buffer overflows. We have control of EIP. We can put stuff in the ESP. If ASLR was not enabled, what could we do right now? In other words, if ESP crashed to the same address every single time, what could we do?
We just write directly to that address, whatever we want.
Close, right? Right. With ESP, we would definitely fill ESP with our malicious payload. I totally agree with you there. But I would just tell EIP's value instead of being 42, 42, 42, 42 to be 01BA745C. Does that make sense? I would just replace EIP instead of 4 Bs and just have it be this. Does everybody understand that? If there was no ASLR enabled, if we did not crash to a different location every time, then we wouldn't have this problem. We could just point there. But We can't. So what can we do? What we need is we need to find, you know, do you guys remember when you like import socket into our code or you import requests, right? You're importing modules that other people wrote. It turns out that this happens at the operating system level as well. These are called DLLs. Have you ever heard of this term DLL? So applications themselves rely on other modules that exist for certain things, for certain resources. The same way that like, I don't know, a fitness tracker on your Apple Watch would need access to the health kit information inside of your Apple Watch, right? Like it just like, that's just how things need information from other things. So what's happening though is when we run the SyncBreeze application, there are other applications that are loaded up alongside to help SyncBreeze do what it's got to do. This application has its own code segments as well. What we would want is what if we could find a naturally occurring segment of code that has dep and ASLR disabled, meaning a place in code that always boots to the same location, some library that always loads to the same location, that maybe has an instruction that we can use at the assembly level to help us accomplish our goal. So here's our goal. Our goal is to have EIP eventually point to ESP, which will contain our malicious shell. But right now, we can't tell EIP to point to ESP because ESP is changing every single time. So instead, what we're going to do is we're going to find a hex or opcode equivalent that will allow us to provide the instruction to EIP to look to the location in ESP, sort of like a variable. Like when X is 5, it's different than me saying, you know, if I say X is 5 and then I try to say Y is 5, that's different than me saying X is 5 and Y is equal to X, where Y would always now be what X is. Right? So that's kind of what we're doing here. We want to find a place in memory where there is a sort of module that maybe contains an instruction for ESP. So we're going to use another tool for this called NASM, so MSF NASM shell. And all this does is it converts instructions from assembly into their op or hexadecimal equivalent. And so the instruction that we're going to be looking for is this instruction called jump, JMP, ESP. What this means is I want to jump to the location that is found in the ESP register. If we could find such an instruction set, right, then we would have this guarantee that if we ran this instruction set at the time, like if we could fill EIP with a location that contained this instruction set, right, then we would jump into the place in memory where what's it called? Where our malicious payload will be. So the idea is, 1, we have control of EIP. 2, find a place in memory that contains the instruction jump ESP. 3, put our malicious payload in ESP's location. Then direct EIP to look at the area in memory that says jump ESP. That will cause the jump to ESP. That will cause the trigger of our payload to go off. Okay, that's the idea. That's the game plan. And so let's look at this. So I'm going to run jump ESP. This is going to come back with the opcode FFE4. And so I'm going to keep that in mind, that I'm looking for FFE4. Okay.
Corey, can you make this a little bit bigger so it's easier to read? Thank you. Appreciate it. Oh my God.
I mean, that's all I need this one for. Okay, cool. So I'm just joking. So this is great. So now let's go back over here. And what we're going to do is we're going to see what modules have been loaded alongside of this application. So I'm going to type in the bang symbol, exclamation point, Mona modules. And so Mona is sort of a script that's going to help us look at what are the related modules. I can't make this any bigger. So this is in your lab manual. It says bang symbol Mona modules. And I'm going to click enter. Okay. And when I do that, we get a list of all of the modules that are loaded into memory alongside of this one. Okay. Now this looks like a big pain in the butt to read through, doesn't it? But what we need is a module, and you're guaranteed to have one. Okay, you're guaranteed to have one on your OSCP, where dep and ASLR are disabled, and it contains no bad characters in its address range. Okay, let's try that again. So let's take a look at these DLLs. You'll notice that there's a bunch of these trues and falses. All of these trues and falses basically mean whether a memory protection is in place or not. You want a DLL that has 5 falses, or at the very worst, 4 falses followed by 1 true, okay? Because this last one just tells you whether it's a built-in DLL or not. So this doesn't matter as much, but 5 falses is as good as we can get. So are there any of these examples here that have 5 falses? I don't know if you can see.
Yeah, that's pretty much impossible to read through the screen.
There you go. So this will be better. Are there any examples here that have 5 falses?
Like fourth to last one.
Yup. Here's one, and here's another. Okay? Now, you need to also remember that we're in a 32-bit OS. Okay? So these are the memory addresses right here. And these are the memory addresses. Now, if we go up to the top, this will tell us that this is the base pointer, the top, and the size. So let's look at the base and the top. And if we look at syncbreeze.exe and we look at libsp, right? What do you note about this column right here? Sorry, this column right here versus this, the top of each of these sections in memory. Look at this location. Do you notice how this location is 0040 and this one is 0046, right? Do you see that? That tells me that there will always be a 00 in this entire range of operations. And what do we know about 00? This means that
Character.
it's a bad character. So we don't want EIP reading the 00, do we? No. So what we would hope is if we look at libsp.dll, you'll note that we do have the same problem at the bottom, but there's a very large chunk of this entire DLL that does not contain 00. Do you note that? Okay. So for that reason, and that reason alone, I'm going to go with the libspp.dll. And I'm going to search inside of this DLL for an instruction, FFE0 or jump ESP. So now I'm going to go back and tell Mona, and I need to look up the exact because I always forget exactly what to say. Thank you, Chris. Chris is sending it to everyone. So now I'm going to tell Mona that, great, I want Mona to find and use the -S option, search. Thank you for putting it there, Chris. XFF XE4, the opcode jump ESP, right? And I want you to do so in the module libspp.dll. Find me a location, right, in this module who has all protections disabled that has a naturally occurring instance of FFE4 or jump ESP. I'm going to search for that. Wow, did we get lucky, right? Look at this. We found 1 pointer and exactly 1 pointer. But where is this found? We found it at 1009C83. Okay. All of this stuff disabled. We got 1 pointer. We got 1 chance. Okay. So I don't know why I can't copy to clipboard address. Okay. So now we have this address. Okay. Is everybody with me so far? So I'm just looking for a naturally occurring jump ESP. That's it. That's all. Okay. How we did this, go to your textbook if you don't remember this. I want you to just understand the point. We need to find where this instruction exists, and we need to make sure that instructions are disabled. Okay. So I'm going to use this button right here. Sometimes you have to push it twice. And I'm going to paste in 1009C83. And I'm going to click OK. And take a look. It brought me in memory, right? Let's make this full screen, to location 10090C83. Does this make sense? This is a naturally occurring jump ESP location. it contains no bad characters, and therefore this is going to be our target. So what I'm going to do now is I'm going to take this address, I'm going to copy this address to clipboard, and I'm going to go back to my code and over here and nano on my POC again. And I'm going to replace my EIP now. And instead, I'm going to replace this with the things that we just saw, right? We saw this, okay? Nobody correct me. If you know what I'm doing wrong, I'm doing it wrong on purpose, don't correct me, okay? So I'm going to put this in here, okay? I'm going to save, okay? And what I'm going to do, okay, is I'm going to run this again. And if all goes well, right, we should jump to our location at EIP, should jump to here, 10090C83, because I wrote into that, right, that location, which always is the same. This is always going to be loaded into the same location. We don't need to worry about that. All protections were disabled, right? Okay. Then it should read jump ESP and jump to this location. So at the end, when our application crashes now, EIP should read 01BA745C and ESP should read 0 or whatever. They should both read the same thing, is my point, because we should both basically, EIP should be pointed to whatever ESP is. And I'm also going to turn on a breakpoint over here so that we can watch it happen. Oh, I of course have to restart this whole thing. So let me just do that again. Start, rerun the immunity debugger as administrator. Again, oops, I gotta attach this to sync, freeze, release the process, go to this location. Sometimes you have to do it twice. There it is. Right click breakpoint, toggle breakpoint. Okay. So if all is good, we should pause when EIP is 10090C83. Make sense? I'm going to go back and once again run this. Oops, I'll go up twice. Run it and let's go back. What happened? Wait a second. It didn't pause there, and EIP is not what I expected it to be. Instead, we got this. Wait a second. How does that make any sense? Let's go back and compare this, shall we? This is what we ended up getting. How are these related? Anyone else think this is weird? As if this whole thing wasn't difficult enough, there's another trick to this whole operation. See, this 32-bit operating system is encoded in Shikata-Ganai, and in this case, it follows Little Endian format. So basically what's happening is the EIP register, and you didn't notice this before because we were just using Bs. So 4 Bs, forward and backwards is just 4 Bs, right? But what's happening is the EIP register is being processed in reverse. So we actually need to flip this information. And so we're actually going to do that just like it says above. So in this case, I'm going to input this as X83, X0C, X09, X10. And now let's restart. Let's save it. Let's go back, restart our service one more time, and let's watch some magic happen. Okay, this is cool because we're getting really close now, right? So let's watch. I'm going to right click, run as administrator, open this up, attach sync breeze, release the set my breakpoint so that we should get to this point. I'm going to set a breakpoint, toggle F2. If you have a Windows machine, you can just hit F2. Okay, I'm running the application. I'm going to come back, double check everything's good. And I don't think it matters, but I'm just gonna, I don't think it matters, but I'm gonna capitalize this anyway. Okay. And I'm gonna save, run this. And look at this, 10090C83. It paused itself exactly here. EIP, just like Ron Burgundy, is reading the teleprompter exactly as expected. I'm going to step into this once. So I'm going to click jump ESP and watch EIP, watch ESP. I'm going to step forward and look. EIP and ESP now match, right? And EIP is going to just start reading forward. So let's go forward. And it's just going to go and read. And we're now in our bunch of Ds. That's where we are. We're in D 44. Remember, that's our D, right? So now this is where we would put our malicious payload. Everything is set up. Look at this. We don't even, like, you were probably thinking we need the payload way earlier. No, no, no. The payload's the last thing we need. We need to make sure everything is going to work. We can fit the payload. We can get to the payload. Now it's just going to be plug and play with a payload. Set up our reverse shell and we're freaking in. That's it. All right. All right. So for the next 35 minutes, okay, so until 5 o'clock, I want you to replicate what we just did here. Okay. I want you to get up to the point where you can identify the 5 falses, understand the bad addresses and how they match your bad characters, find the opcode within Mono modules that you need, right? That, and using the NASM shell for jump ESP, right? And be able to actually update your code to include this, okay? I want you to have code that properly redirects you to ESP, okay? Does that sound fair? Okay, so you know what, maybe I'll give you, let's see how you're doing in 30 minutes. If you need more time, we'll give you more time because this is gonna be, this is a little bit harder. I want you to get comfortable with this part, okay? All right, y'all got this? Any questions before I let you go into it? All right, keep crushing it. Put in tickets if you need help. Zoom recording. Okay, so here we are doing stuff, and so let's go back. I've attached this. I'm gonna let the application run. It's running. Let's go back to talking about where we were at. So, okay, clear. So, if we go back, we're at the point here where we have gone ahead and we've run our vulnerable application and attached it to immunity. We've ensured we have a script that can communicate with the target. We've performed fuzzing. We've figured out what registers are overridden, right? We found out EIP was cleanly overridden. We found the bytes at which EIP was overridden. We found the offset with another register. And we verified that we have enough room to fit a malicious payload. We then went and determined bad characters. We then went ahead and worked on redirection. So how did we like find a DLL that would like point us to our area in memory? And we used Mona for that. That was the last thing. Make sure you look for at least 4 falses, hopefully 5, but you need at least 4 falses. And then finally, and by the way, not any 4, the first 4 have to be false. And make sure the memory address range does not always have bad characters. So that's a really big thing to look for, okay? The next step is generate the payload and update our exploit code. That's it. So now what we're gonna do is we're gonna go back to our code, and you see where we have this whole section for data in ESP? Well, between data in ESP and filler, sort of at the beginning here, we're gonna put our malicious payload. Does that make sense? We're gonna replace all these Ds with actually our malicious payload. So let's go ahead and actually do that. I'm gonna close out of this, and I'm going to use MSF Venom. And let me just look up the syntax for bad characters. I think it's like -B or something, but it's like
-B.
Yeah. Let me just yeah. So I think okay. So we're gonna use MSF Venom -P Windows shell reverse TCP L host equals what the hell is config. Okay. L port equals 443 -F. C dash E, actually dash F, we could just do PY even. And then it's encoded in Shikata Ganai. I don't think you need this, but I think that's the default. I'm not even gonna specify it. And then you need to specify your bad characters. So by the way, this is, everyone knows this, like this isn't a surprise, right? You all understand this so far? I'm not, like this isn't the first time you're seeing this. So I'm basically generating a Windows shell reverse DVCP, which by default is 32-bit. Lhost right here, my IP address, lport, the port I want it to call back on. I'm just specifying format Python so I can just drop it right in. And then in terms of bad characters, I want to specify all of the bad characters that we have actually seen. So it's like comically large. Let me go to like one of these. Clear. And let me nano on my POC. And okay, so I'm going to copy this list of bad characters. Copy. And I'm going to, actually, you know what, before I even do this, let me show you this. So if I don't do this, take a look at what I'll get. Okay, notice these 0 zeros, right? So we have to specify this so we don't get these bad characters. Now let me add in my bad characters, dash B, X00. Oh, no, I think I copied and pasted it actually. Here it is. Okay. And we've gotten a buffer. And does it tell me how many bytes it is? It does. It tells you it's 351 bytes. Okay. So here's my buffer. Why can't I? Okay. Okay. All right. I see you. I see you there. Copy. All right. Let's go back. And let's go ahead and include my buffer. So I'm going to say my buff is equal to, oh, actually, no, I think I just got to paste it. Yep. So we have my buffer. All of this is my buffer. Okay. And now I want to make sure that my data, so my input buffer should now include my buff. Right? Is that what we called it? And we want to also make sure that we subtract out the length of the buff. Don't screw up now because of this, okay? Because you forgot to account for the size. At the very least, try to subtract out the number that it gave you, which was 351. If that doesn't work, so length of buff minus the length of the filler. Okay. Questions? Okay. So this is going to sound a little bit strange, but this is one of these things that it's a process thing. So what's happening is our EIP is going to jump to ESP because it's going to hit that instruction set that says jump ESP. Does that make sense? From there, what's going to happen is EIP is going to do a lot of work on this payload. And this payload is encoded with Shikata Ganai. In other words, the payload is encoded in a hexadecimal format that is not usable. It needs to be decoded. The way that this often works is that the data or the space around the payload as it's being decoded will be filled up with the payload. In general, this happens before the payload. So what could happen is, in this case, our buffer starts to decode itself before like where it runs, and EIP starts past the point of where it runs. So long story short, if we do it like this, it's possible that our payload actually won't execute. It would be as if we like started, imagine this is everything you need for a payload and we started here. It's like, well, then obviously that's not going to work, right? So what we actually want to do is we want to have a way of adding a little bit of space or buffer area for our malicious payload to use. And so what a lot of people will do here is they use something called a NOP sled. So I'll show you this. This is called a NOP sled. And all I'm going to do is I'm going to create X90s which is a no operation code, hence NOP, no operation. And I'm going to include 16 of these. These will create this won't create any issue. And we have plenty of extra room. Remember, we had 500 bytes to spare. So we're going to just use 16 bytes for no op codes so that we can be sure that our payload will have the space that it needs to decode before the sake that it gets used. It's a more complicated discussion, but anyway, include this NOP sled. Again, I'm going to go back over here. I'm going to subtract out the length of my NOP sled. I'm going to also include my NOP sled and my buffer. Okay. Okay, I'm going to save. All right. I'm going to also, of course, set up my listener. Yeah. Okay. I'm back over here and I'm going to make sure that this should be running. Immunity is running. I'm going to even set a breakpoint here so that we can, oh, that's not right. Breakpoint here so we can even see this happen. Okay. And let's hope I didn't screw anything up. No. There it is. Okay, ready? Let's do it. Running it. Okay, I shouldn't have a shell yet. Good, okay. It should have crashed to the location we expected. It did. Yeah, EIP is at the location that we expected it to crash at. I'm gonna step forward 1 and I'm gonna enter our NOP sled. You see this? All these no-op operations, giving it room to decode. And I'm gonna release, let it finish. And now, if I go back, take a look, we have a shell. Pretty crazy, right? Always still feels good, right? So you know, and I can give you an IP config to prove that that's that remote machine, right? So here you are. Pretty cool. Pretty cool. So the long story short here is like, we do all of this work. The payload's the easy part, right? This is the easy part, I think, right? Like adding in this part is the easy part. The hard part is identifying the bad characters, finding where EIP is, all these other steps. But it all gets to the same purpose of including this malicious payload. Vinny, it's super easy. Well, I mean, everything's easy with enough practice. So make sure you practice this, okay? So we have, you know, I'd like for you to take the next 20, 25 minutes to finish this with your partner. I want to bring us all back at 5:40 because I want to wrap up by talking about some like my strategies for like how I would, if I'm you, like what I would be doing to study for the OSCP, if that'd be helpful. And you know, how to get you all ready for that. And like I said, I think that the most important thing that you can do, at least in the short term with this information, is practice it, because it is methodical, it is repetitive, it is the same thing every single time. Proof of concept 1 is very similar. Proof of concept 2 is a little tricky, just FYI. There's a little bit of ROP chaining involved, but we can talk about that another time. For now, let's finish up, you know, infiltrating the sync freeze application, and I'll bring us all back together at 5:40 for any questions that we have. Okay. Are there any other questions before I let you go? Anything on like what I just did, or how to generate that shell payload, where to put the shell payload? Okay, good. Put in tickets if you need help. I'm here. All right. Bye-bye.